Newton's second law with friction, example 2. You have an 85 kilogram crate being dragged across the floor, horizontal flat floor, with a rope. Here's the free body diagram. The 85 kilogram mass, force of gravity straight down. We'll take the easy route, 85 times 10. So the force of gravity, the weight, is 850 newtons. And the support force, or in other words the normal force, is also 850 newtons. Now there's a rope pulling to the right which has a certain tension. It tells you the tension here is 285 newtons. Make a note of that. And there'll be some friction restricting the motion. Force of friction. In this case it is kinetic friction because it's sliding. Now the nice thing about this problem is that there's a constant velocity. These are almost always the easier type of problems because when you have constant velocity, what that means is the acceleration is 0. And therefore the F net, which is m times a, is also 0. F net equals 0. Which implies that all the forces balance out, the 850 down with the 850 up, but more importantly here, the force of friction equals the tension. So in other words, the force of friction here is equal to the 285 Newton tension in the rope. You might say, well then how is the crate moving if the two forces are equal? Well, this means that there must have been a force a little bit greater than 285 newtons of tension in the rope to get the crate moving, but once it was moving, if you just maintain a force equal to the force of friction, you don't accelerate anymore, or you don't decelerate, you stay at that speed. But yes, you would have needed a force greater than that to get the crate going. That would have been the F net originally. But for now, it's just moving at a constant velocity. Doesn't matter whether the constant velocity is 12 meters per second or 500 meters per second. Those two forces must be equal. Example 3. Here we have our 75 kilogram parachutist with all the equipment and so forth. Once again, you don't need to get fancy. You can draw a square. That's the person with the parachute and everything else. Gravity is pulling them down. Force of gravity here, which is going to be roughly 750 newtons. The mass, 75 times 10 meters per second squared, gives me a force, a gravity force, a weight of 750 newtons. All right, there's no upward normal force now because you're not sitting on a floor. However, there is an upward frictional force, force of air resistance. I'll call that F sub air. Now in part A, once again, it's relatively easy, like the last problem, because you have the constant speed. Wouldn't matter what the constant speed is, but it's good for the parachutist that it's a pretty low speed because you need to land safely, and a 6 meter per second speed is, I guess, safe enough to land without breaking your legs or killing yourself. But in part A, the problem is easy, like the last problem, where the acceleration is 0, therefore the net force is 0. Therefore, the force of air equals the force of gravity. So the force of air resistance is 750 newtons. All right, that's easy enough. However, now a bad thing happens. This person's in a little bit of trouble because the parachute develops a rip. Hopefully they have a second parachute or something, but we don't know anything about that. This is just an illustration anyways, obviously. So they start to accelerate downward. It's the same free body force diagram, so we can refer to the same diagram. But now we do have an acceleration, and we have an F net equals ma. We have an F net equals ma. Once again, like we learned a couple days ago, the net force is the combination of all the forces. When you have two forces, you take the big force and either add or subtract the second force. If they're in opposite directions, you subtract them like you would do here. The bigger force must be down because you're accelerating down. 750 minus the force of air equals the mass of this parachutist times A. Now the problem is, what is A? We have two unknowns here in this equation, the force of air and A. However, there's extra information, as you can surmise here. We can go back to the uniform acceleration equations, v sub I, v sub f, a, s, and t. That's a fail-safe way of doing it. Or you can just go back to the simple definition, which is really, I'll do it up above here. A equals delta V over T, which is really just the first uniform acceleration equation in disguise. Not really even in disguise, it just is the first uniform acceleration equation. The acceleration is the change in velocity, which is 10. Check your units, meters per second, that's good. That's the increase of 10 meters per second from 6 to 16 meters per second in 3.2 seconds. So the acceleration here is 3.1 meters per second squared. Sorry, that's a 3.1. So we're going to plug that in for A, and then we're almost home free here. We're home free, the parachutist is not. 750 minus the force of air equals 75 times 3.1. That's 3.1 there. And if you just punch that all in your calculator, you get the force of air force, the air resistance force is 517 newtons in the upward direction. Last thing I want to say that don't let the phrase the average upward force deter you at all, because with a flopping, ripping parachute, the air resistance force is going to be somewhat variable, and your speed is going to be changing here, affecting your air resistance force. But they're just basically telling you in this problem, find the force of air resistance on average for this particular scenario. And the answer is the 517.